Okay, so this is 17.4, Green's theorem. So this is our first of our really big theorems from vector calculus. Today's going to take place completely in R2, so in the plane. So this is going to be a theorem that is, in a way, a version of a fundamental theorem of calculus for vector calculus. Knowing how important the fundamental theorem of calculus is, you can expect that this is actually super important as well. All right, so we're going to start with two definitions. So the way we're going to do this is there's two versions of Green's theorem. At least our book likes to pitch it this way. One of them is, in a way, more traditional or traditionally covered than the other, but we'll talk about that when we get there. All right, in order to talk about this, we need to, like I said, it's kind of a fundamental theorem of calculus for vector fields, or for vector calculus. So let's start with a vector field. So this again is in the plane. So these are all x comma y, q of x comma y. All right, so we have a vector field, f, and let me just emphasize, right, everything is happening at all the points, or at points in a plane. We're breaking down f into its two component functions, pi plus qj. Our book uses f equals little f comma little g, but the reality is that if you pick up almost any other calculus book, they'll use P and Q. It's almost even standardized at this point. So I'm going to use P and Q. I don't know why our book use F and little f and little g, because it's super not standard. Okay, so let me define, given these two vector fields, let's assume that, so for the entire lecture, assume P and Q have continuous partial derivatives. All right. This is to make sure that things can actually be differentiated, and then after they're differentiated, they actually have nice properties when we actually start to work with them, integration and stuff like that. All right. Okay. The first definition relating to this vector field f is the divergence. So this is the divergence of f. And what happens is, this is a kind of an operation that you can do on a vector field, that you put in a vector field and you get out a function. All right. And the function is going to be dp dx plus dq dy. All right. So that's the definition of the divergence. So notice again, it's a function. All right, so it's no longer a vector field, it's a function. All right, so our Green's theorem will have something to do with this. There's another quantity that we want to talk about, and that's the curl. So we'll talk about the meaning of what these guys are after we write down the our theorems. Because our theorems, essentially, one way you can look at it is that our theorem tells us, the Green's theorem tells us the meaning of the divergence and the meaning of the curl. All right, because on the face of it, there's no reason to expect that dp dx plus dq dy has any meaning, right? Why isn't it dp dy plus dq dx, right? Why isn't it dp dx dy, right? Second derivative, plus dq dx dy, right? So these guys here that we write down actually do have very important physical meaning. All right, so the curl is going to be the coefficient. So let me describe it like this. the curl in 2 dimensions, so we're in the plane, is going to be a function as well. All right, so this is going to be a function, but there's a huge kind of disclaimer in higher dimensions. We're going to have this concept. Actually, it's the point of 17.5 is to extend the idea of divergence and curl to higher dimensions. In higher dimensions, curl of f is a vector. All right, but in 2 dimensions, you can kind of, in a way, cheat a little bit because the vector that it's supposed to be actually is always actually in the k direction. All right, so here's how you actually calculate the curl, and we can see that that's the case. So curl of f is you do ijk. So this is just a kind of a mnemonic to help us remember how to calculate the curl. ddx, ddy, ddz, and then we put p, we put q, we put 0. All right, and we calculate this this determinant, and what we're going to get is I times so ddy of 0, which is 0, and then ddz of q, which is 0, because q is actually just a function of x and y. All right, so in a way, what we're doing in this computation is we're extending our vector field into the z domain just by just like extending a cylinder from the xy plane to the z to space. Okay, and again, this looks like overly complicated, but I'm doing it like this because it will mirror exactly what we do in 17.5. All right, so there'll be some sort of consistency between these 2 sections. All right, minus j, and then j to ddx of 0, and then ddz of p depends on just x and y, so plus 0. All right, and then finally plus k, dq dx minus dp dy. All right. Okay, so ultimately what we can see is using this procedure for calculating the curl, we just end up with something in the k direction always. All right, so always in the k direction. So in a way, there's no point in thinking of it as a vector because it's always pointing directly upwards, right? So for the purposes of 2 dimensions only, for the purposes of the plane only, we just take this part right there. All right, so curl of f is equal to that part, dq dx minus dp dy in plane. All right, just to emphasize that. Okay, so that's our formula for the curl. Again, it looks weird. Why would we care about this particular combination of derivatives of q and derivatives of p? But we'll see the physical meaning in just a few minutes. All right, in terms of computation, it's just as easy as it seems, right? Whatever function p is, you take dp dy. Whatever function q is, you take dq dx, right? You subtract the 2, and you've got a new function. That's the curl. All right. Okay, so let me emphasize this is a function. So again, you've started out with a vector field, and now in the plane case, you have a function for both the divergence and the curl. All right, so let's actually start to move towards our fundamental theorem of calculus, or Green's theorem. And the way we're going to do this is we're going to start with specific kinds of regions. So let's start with region. Let me just draw a picture. We have a region R, and we have its boundary curve C. All right, so R is equal to region, and again, in the plane. Right, I want to emphasize that heavily because we're going to be doing versions of these functions not just in the plane, in the very, very near future. So in the next few sections, actually. So this, for today, completely in the plane. So R is a region in the plane, right? Perhaps the inside of a circle of radius 9, right, about the origin. And C is equal to its boundary. Okay. Now, we're not just going to leave it at that. We actually want a closed, so we want, let me emphasize here. So C is equal to closed. All right, so it has to close up on itself. Otherwise, it's not going to enclose a region. And you kind of expect that we want this because we're going to be doing integration, right? So we want to do a region that we want to integrate over. So closed, piecewise smooth. What does this mean? So this means that very, very, very roughly, we can parameterize these guys with a parameterization that has as many derivatives as we need, except at discrete points. So you're allowed to have something like this, right? A region like this, and then like that. So these 2 points right there are actually kind of problem points, but in a way it's not going to matter because we can integrate this region and that curve region separately. All right, so that's why the piecewise. Okay, so piecewise smooth, oriented. So we want these regions to be, or we want our curve to actually have a direction, and not just oriented, but oriented counterclockwise. All right, so in this picture, we want to associate the direction, this guy right there, to our curve. All right. Now this oriented counterclockwise is slightly uncareful in a way, slightly sloppy in a way, because we're allowed to, at the moment, we're allowed to work with regions that look like this. So the region, this kind of annular region like this. So R is this guy right here. Okay. In this particular situation, C would have 2 pieces. All right. So C would have one piece is the outer boundary, and it would be oriented in that direction. But the inner boundary would be oriented in the opposite direction. All right. C equals 2 pieces. So this is actually really useful. It's not just a small technical thing. It's actually useful. You'll see this when you take differential equations. Green's theorem is actually going to be a very important theorem that you use that can help you solve certain kinds of differential equations. And in many of those cases, you need to integrate on regions where you're missing a hole inside the region. And the reason you have a hole in your region is because the vector field might not be defined in that hole. All right, so you're not even allowed to work at that hole, and so you're forced to work with a region that looks like this. All right, so 2 pieces C1, comma C2. Let me call this one C1, and let me call the inner one C2. All right, so C1. So let me just put it as a note. C1 is counterclockwise. But to keep things consistent, C2 is actually clockwise. Right? So this kind of oriented counterclockwise is slightly sloppy. All right, maybe a better way just for R2 to say this is that, let me write it like this better with a question mark, because most of the time, 100% of the time, everybody understands what you mean when you say oriented counterclockwise. All right, it's just that technically, it's not necessarily 100% correct. All right, so let me write better. Region is on left of curve. Okay, what I mean by that is if you're driving along this curve, thinking of it as a road, right, the region is on your left as opposed to your right. Okay, so you can see that that's the case for both C1 and for C2. Okay. All right, I'm still just going to say oriented counterclockwise because, again, everybody knows what you mean. It's just there is a technicality that you have to be aware of, and it's actually really, really important because if you orient C2 in the wrong direction, then and you apply Green's theorem, it's going to be incorrect. All right, so these are the kinds of regions that we're going to be working with in this section. All right, so what I want to do is I want to integrate over this region. I'm going to be integrating the derivative of f, and by derivative I mean either the divergence or the curl. And then the result of that integration is going to be something that happens on the boundary. All right, so let me actually start with the most simple region, a rectangle. Okay, so this is my region R. All right, its boundary is piecewise smooth. So there's 4 pieces which are nice and smooth, right? No sharp corners or anything absolutely terrible happening. We orient it counterclockwise, so this direction, right? So let me just draw all 4 arrows. So this is my curve C. It consists of, again, it consists of 4 parts. All right, so if you did the extra credit problem on last week's homework, you were asked actually to literally show that this integral here over the region R of the divergence of f dA is equal to the line integral over the boundary C f dot n ds. All right, so this was the extra credit last week. Okay, if you didn't do that, you probably should. Very, very straightforward. In fact, super, super simple. All right, if you just literally write out the derivative on the left-hand side, write out the definition of divergence. You're integrating derivatives, so you can apply the regular one-variable calculus fundamental theorem of calculus, and then out will pop the right-hand side if you interpret it in the right way. Okay, so this is true, and this is essentially the statement of Green's theorem, except of course we've restricted ourselves only to a simple domain of R equals to a rectangle. All right, but before we actually talk about more interesting regions, let's look at all of this, these features, or this expression here. So first of all, sorry. All right, first of all, this left-hand side is a perfectly legit double integral. It's a double integral of a function, right? Divergence of f is a function. The region is just a region in the plane. All right, so there's nothing interesting or fancy going on the left-hand side. On the right-hand side, we have f is a vector field. F dot n ds, we talked about that in the last sections. And of course, if you just think of it as f dot n, then that's just a function, and you're integrating a line integral over your curve. All right. However, you can also think of it kind of in a way more natively as a line integral of a vector field. And by the way, this n right here is the outer normal. Sorry, this n is the outer normal. Right, so n actually points this way. N points this way. Right? Why is it the outer normal? Because we oriented our curve counterclockwise. Right? So remember, if you do want to calculate n, you take your direction of your curve, t, and then you cross with k. All right? So for example, on this vertical portion right there, t is pointing upwards, right? And k points outwards toward the screen. And so when you do the right-hand rule, you're going to get n pointing outwards. Okay, so this is the outwards normal. And again, it is only the outwards pointing normal because C is counterclockwise. All right, so our choice of orientation of C matters, and that's exactly where you can see that it matters. Okay, by the way, this right-hand side we said was the flux. Right? So the interpretation of it was how much stuff is moving from inside the region to out of the region. Okay, so if it's a positive number overall, across the boundary, right? So overall, if it's positive, that means there's more stuff moving out of this rectangle than there is moving in. And if it's negative, there's more stuff moving into the rectangle than moving out. And by stuff, I mean, stuff determined by the directions of the vector field. Okay, now let's extend this to general regions, and then we'll go more deeply into how this idea of flux tells us about the meaning of this divergence F right there. Okay, so obviously we can't just only restrict ourselves to working with rectangles. What about a regular region that looks like this? So what about general regions? All right, so let's say we have a region R that looks like that's like this, the inside of this guy right here, and we have C as its boundary, oriented counterclockwise again. Can we write down a theorem that looks similar? And the idea is yes, we can actually write down the exact same theorem. And the reason is because just think about what we do when we do integration. We chop our region up into rectangles, right? So I can chop this guy up into tiny, tiny little rectangles. So let me actually kind of do that. Right? And what we do is we add things up over these rectangles. Okay, so we can actually kind of extend Green's theorem from the rectangle case to the general case by thinking of this idea. So let me take just a few of these rectangles to see what's going on. Let's take, for example, these three rectangles. Let me draw them down here. All right. So here's a rectangle. Here's a rectangle. Looks kind of something like this. All right. Okay. So we know that Green's theorem is true on each of these rectangles. Right. So what we have is on the first rectangle, let me actually write them all down. So double integral R1 divergence F is equal to integration on its boundary. Let me call this C1 for now, right? F dot NDS. All right. Okay, but what I'm going to do here is I'm going to actually break this guy up into each of its component pieces. So let me call this one, or call this curve A, call this curve B, call this kind of boundary curve C. I guess I shouldn't use C. Let me call this D, and let me call this one E. All right. So this is actually equal to integral A F dot NDS, right, plus integral B F dot NDS, plus integral D F dot NDS, plus E F dot NDS. All right. Okay. Now let's look at R2. Let's look at rectangle 2. So in rectangle 2, we have the same idea. R2 divergence F. We have the same theorem equals, right? Again, this is from the extra credit problem. C2 F dot NDS. Right? And what is this? This is equal to, well, let me write down some curves. Let me do it like this. Let me call this, I stopped at E, so let's call this F, G. This is not good. Let me call that G. And then the next one here is E, but in the opposite direction. All right. Let me call that H for now. But it's really important that it's the opposite direction of E. And I. All right. So we have F is probably not the best name, but too late now. G, H, and then I. Right? Okay, but look at this. When we're integrating the E integral up here, we're integrating from left to right, right? When we're integrating the H integral, we're integrating right to left, right? And another way to kind of think of this is f dot n, right, for the E integral is n is pointing downwards, right? Whereas for the H integral down here, because we're moving counterclockwise, n is pointing upwards. Okay, so if we think about the f dot n ds as flux, as how much stuff is moving across the boundary, right? For this first one, over E, we're thinking about how much stuff is moving across the boundary from the left side of E, from above to below, from up here to down there, all right? For H, we're thinking about how much stuff is moving from down here to up there, okay? So they're actually opposite numbers, all right? So what happens is when we, if we add together these two integrals here, these two guys are going to cancel. All right? Because again, one of them you're going left for R2, whereas for R1 you're traveling to the right, and so those two integrals will be the opposites, and so they'll cancel. All right. So if you think about it, at this moment we just have two rectangles. Forget about R3 for a second. What we've actually just shown is that if you want to do a double integral of the divergence of f over this entire region here, right? It's going to be the right-hand side, which is f dot n ds at A, which is this one, plus at B, plus D, and then E and H are canceled, right? And then what's I? I is down here like this, right? F is like this, and then G is like that, all right? So that's actually the full integral all the way around, okay? So we've essentially proved Green's theorem in that we can place two rectangles one on top of the other. Okay, so now imagine what happens when we add a rectangle 3, right? When we do the Green's theorem for rectangle 3, it shares, let me draw it down here. So rectangle 3 shares one side with rectangle 2, right? And let me see what I called it over there, G. Right, so for rectangle 2, that was upwards in the G direction, right, when we integrated. But for rectangle 3, again, as usual, if we want to write down Green's theorem, we're going counterclockwise. So to the perspective of rectangle 3, we're integrating downwards. All right. And so again, when we write down the Green's theorem expression, these two guys are going to cancel out. All right, and so what we ultimately end up with is that Green's theorem is true over this region. Okay, because all we're doing is we're just adding up divergence f over R1 plus divergence f over R2, and that covers this guy up here, and then plus divergence f over R3, that covers this guy here, right? That equals to the right-hand side stuff, but the right-hand side stuff is all going to cancel out in the interior portions of these rectangles. So you're going to end up with, on the boundary, right, you're going to be going here, you're going to be integrating that, and that, whereas the two dotted lines inside, those are going to just cancel away. And so you can see ultimately you're integrating all the way around the boundary. All right, so this works for 3 rectangles. And of course, you can now clearly imagine that if I just have a general region, the general region is essentially just made up of tiny, tiny little rectangles all added up together, right? And so the Green's theorem is true for any region that we like, just by kind of doing smaller and smaller rectangles, and then of course taking a limit, and then carefully working in that way. Of course, as usual, we're glossing over a lot of serious math here, but I think this is a good enough discussion for our class. Okay, so hopefully that gives you an idea for why Green's theorem is true. So let's actually write down Green's theorem again, the actual statement. So this is the flux version, or this is what our book calls the flux version. All right, so it's double integral divergence f dA over any region. That, of course, satisfies the properties we talked about earlier, smoothness and all that kind of business, equals to a boundary, f dot n ds. Again, everything is oriented clockwise in quotes. This is the outer normal. All right. That's convention very much, the outer normal. Okay, and that's it. That's Green's theorem. So outer normal is like this, right? This is our region. This is our C. Okay, and again, what is the divergence of f? More literally, it's dp dx plus dq dy. All right. Okay, so now let's finally see why we actually have a name for this strange looking quantity. And it's basically, or at least the way we're going to discuss it, is it's kind of encoded in our expression for Green's theorem. Okay, but before we actually step to that, this is a version of the fundamental theorem of calculus, because what is the fundamental theorem of calculus? It says integral something like f prime dx is equal to f of b minus f of a from one variable calculus, right? So a to b. Okay, the left-hand side here is you're integrating a derivative over a region a to b, right? So you're looking here. What is the right-hand side? The right-hand side has that same function, but no more derivative. All right, the derivative is gone, and you're not looking at the region, you're looking at its boundary, a and b. Okay, so up here it's the same idea, right? We're looking at the divergence of f. Divergence of f has a derivative in it, right? You're taking dp dx and then dq dy. So this divergence of f, you can think of it as taking a derivative. You're taking a derivative, you're integrating it over a region, right, on the left-hand side. And on the right-hand side, there is no derivative, right? It's just f by itself. And you're looking at the boundary instead of the region, all right? So it's very, very much the fundamental theorem of calculus. And in fact, of course, if you did the extrapolated problem, you literally saw that in order to derive the expression, you're applying the one variable calculus fundamental theorem of calculus. Okay. All right. So actually, let me talk about the other version first before we actually talk about the interpretation of the divergence and the curl. So second version. This is the circulation version. And this is the one that's more common, that you'll see more commonly, for example, in calculus books. Many calculus books don't even talk about the flux version at all, because they're actually the two fundamental theorem of calculus, or these two Green's theorems are actually completely equivalent. So you really only need one of them. And most calculus books, if they only do one of them, they only talk about the circulation version. All right. Okay, so the circulation version has to do with, is the same idea. You have a region, R, you have C, literally the same setup. Okay, but this time this is about the curl. Curl of f over R dA, all right? That's equal to integral C f dot t ds, all right? Okay, so this is the circulation version, because remember we saw last time, in the last section, this was circulation. So it's how much fluid is flowing along your curve, right, in a way. Okay, and again, this version is going to tell us, or examination of this version of Green's theorem is going to tell us, in a way, what the meaning of the curl should be. Okay. All right, and remember again, let me write down here. The curl is nothing too fancy. It's just derivatives of P and Q, right? Actually, I should write down dq dx minus dp dy. So just like with the divergence theorem, this left-hand side is just the integral of a two-variable calculus integral of a function, right? And the right-hand side is circulation. And also remember, there's many different notations for this circulation. I happen to like this one a lot, so I'm gonna use it. But remember, if f is p, f is equal to pq, right? Then this integral is the same as, in terms of just purely notation. No, it's not really mathematics. In terms of notation, this can be written as p dx plus q dy. All right. Or alternatively, f dot dr. All right. So why is this guy true? So there's two ways to see it. One way is to do literally what we did with the divergence theorem. You can prove it on a rectangle, right? And again, you're in this case, you're just working with straight lines. So it's super, super straightforward to prove it. And in fact, it's again, just a regular one variable calculus, fundamental theorem of calculus used twice, all right? Alternatively, you can prove it from, and then of course, what you do is you add up, you take a general region and you break it into rectangles. And you can see it works because for one rectangle, what you're doing is you're doing an integral like this. And if you have two rectangles side by side like this, right, for the rectangle on the left, when you talk about the right-hand side integral, f dot t ds, you're integrating counterclockwise along the curve. So you're integrating like that, like that, like that, and like that. But on the right-hand side, on the right-hand rectangle, you're integrating like that, like that, like that, and like that. All right? So what happens is, again, these two integrals here on the right-hand side would cancel out. And what you ultimately end up with is, what you ultimately end up with is that, which is exactly what you want on the right-hand side, right? Integral on the boundary, okay? And then you just, pile up the rectangles one on top of, one on top of the other or whatever, in order to fill up your whole region, and you've got the proof of the Green's theorem. But again, we can rewrite this. Let me emphasize that the two are the same by showing you that we can derive this version of Green's theorem from the other one. All right. So again, f is equal to p dot q, or p comma q. Let me define a new vector field. Let f tilde. I guess that looks too ugly. Let's let g be q comma minus p. All right, perfectly legal, right? Because p and q are just functions, and p comma q just means pi plus qj, and now I'm looking at qi minus pj. All right, so let's apply the previous version of Green's theorem to g. Okay, and what's going to happen is out is going to pop the Green's theorem for f. All right, so let me leave a space here and let me write this. Double integral divergence of g, so I'm applying Green's theorem, again, the flux version, and again, we're working on a region, counterclockwise on the boundary. So this is R, right? This is equal to, this is the Green's theorem that we already know, the divergence version, C G dot N D S, all right? Okay, but let's look at this. What is the divergence of G? That's a double integral. Divergence is dq dx, d of the first thing dx, plus d of the second thing dy. All right, so that would be d of the first thing dx plus d of the second thing dy. Okay, and this is dA, of course, dA. All right, but if you stare at this, right, this is literally our definition of the curl. This is the curl of f. Okay. Literally, right, the curl of f is dq dx minus dp dy, where f is equal to p comma q. All right, so we have the curl of f is equal to that, is equal to divergence, and then we've applied our flux version of Green's theorem. Okay, and then now let's write down what this guy here means, g dot n ds. All right, so this is literally c. What is g? We said it was pq comma minus p. All right, and what is n? Well, or what is g dot n ds? Right, we saw in the last section you can kind of shortcut the computation of the ds because the n in a way has a r prime of t has a 1 over r prime length of r prime of t, right? And then ds has a length of r prime of t, so they cancel. And so we end up with, in practice, just something like this. Let me write it like this: dy dt, comma dx dt, right? dt. Okay, and I guess I shouldn't say c. Let me just write. So these limits of integrations are with respect to t now, because now we've actually converted completely into an integral with respect to t, right? Let me actually just write it as t equals a to t equals b. All right, just to emphasize again, it's a one variable calculus integral. All right, so what is this? Literally, let's just write out the dot product. This is q dy dt minus p dx dt, and then dt. Oops, sorry. Let's see. This is a minus here. There's a minus there, right? Because this was the normal. Sorry. Dot nds, right? So it's not dot t, in which case it would be dx dt, dy dt, right? This is normal. And so what happens is this minus sign and that minus sign cancel, you get a plus. All right. So if I just reorder this as p dx dt plus q dy dt, right? Whole thing dt. What is that? That's literally how you compute p comma q, right? Dot t ds, right? In fact, if you think about the notation, right, the dt kind of cancels with the dt, right? And that's one of the reasons why you have this notation p dx plus q dy. All right. Okay, and what is this last line? This is literally f dot tds, right? The line integral. This integral is t equals a to t equals b, t equals a to t equals b, right? So at the end, we've converted back to the expression of a line integral. And so ultimately, we have the integral of the curl over the region is equal to the circulation over its boundary. All right. And so let me again write the full version. Oops, sorry. So we have the integral over the full region of the curl of f, which is a derivative, dA, is equal to something on the boundary, integral, or yeah, something happening on the boundary, an integral on the boundary. And then the f doesn't have a derivative anymore, dot tds. So this is circulation. All right. So this is the Green's theorem circulation version. And again, the reason I did this computation just now was just to show you that the two versions of Green's theorem are actually equivalent. And that's one of the reasons why many books only just give you one of them. Okay, and again, like I've said before, this version of Green's theorem, if you just say Green's theorem to somebody, they're probably almost certainly going to be thinking of this version of it. So that's just a small note for maybe future, when you talk about it in a future class. Okay, so let's write them both down and then let's explore what they mean. So the flux version. And the circulation version. Okay, how are we going to explore these? Well, we're going to start with at the point where we know the right-hand sides of both of these, right? So this is the flux, this is the circulation, right? where by flux we mean how much stuff is moving across the boundary, C, because n is the outer normal, across the boundary C from the inside to the outside, right? And circulation is how much stuff is moving along C in the counterclockwise direction, okay? All right, now imagine what happens if we pick, we have our region R, let's just pick one point in R right there, all right? Now imagine I take just a nice simple circle here like this as my curve, and my region is, the region I'm going to be concerned with right now is just going to be this region inside this tiny little circle, all right? Okay, so I can, certainly Green's theorem is true for both of these, for this particular region. And what happens is, if I look at the flux version, what I have is double integral over this region, divergence f dA is equal to how much stuff is moving out of this region across the circle, right? So how much stuff is moving across the circle like that, right? If more stuff is moving out, then positive. If more stuff is coming in, then negative, all right? Now imagine this. I take this circle and I let the radius go to 0. Okay, so what happens is, as I let this radius of the circle go to 0, I'm working with a circle that's closer and closer to my point, right? So in a way, what happens is I'm getting behavior that's, in a way, I'm getting computations. This right-hand side is telling me more and more about what's happening at the point, right? Because if you give me, if you look at another point, right? If I have, this is my point of interest. If I have another point, right? Maybe my first circle includes both, right? But as I take smaller and smaller circles, I'm kind of no longer examining what's happening at this point anymore. I'm still examining what's happening at that point, right? So as I take smaller and smaller circles, the right-hand side, right, the integral f dot n ds is more and more about what's happening at the point in the middle, all right? So right-hand side is, this is very, very vague, more and more about behavior at the center, right? As opposed to overall behavior, right? Again, normally, right, this flux integral, this flux integral is overall behavior, right? How much stuff overall is moving across this maybe big region, right? But now, as my region gets smaller and smaller and smaller, it's now more and more just about what's happening at the center. Okay, of course, you actually have to do some serious math, do some limits to actually conclude this carefully, but this is the general idea. Okay, and so what that means is the left-hand side over there is as you go to 0, right? It's telling me that the divergence, the left-hand side is an integral over smaller and smaller circle, right? And that circle is kind of capturing, less and less of what's going on outside of the point. Okay, and so in a way, this left-hand side is going to what's happening at just the center. All right, so let me write it like this: left-hand side is going to behavior at just center. All right, so same thing, right? Behavior at center, behavior at center. Okay, what's the behavior at the center? That's divergence of f. Divergence of f is a function at the center. All right. Okay, so what we conclude is divergence of f at the center is about, or at any point, right, is about how much stuff is flowing out of the point. Okay. All right, so in a way, it's telling me whether my point is a source or a sink. Okay, so divergence of f tells me, so divergence of f at a particular point tells us where f has sources or sinks. Okay, So maybe this is a little vague. So let me draw a little picture here. Let's say this is my let's say this is my point of interest, and let's talk about a very simple vector field that's just pointing radially outwards away from this point. Okay. Now think about this. The right-hand side integral around a circle is always going to be positive, right? Because things are moving away across the boundary, out of the region. All right. If I do a smaller circle, it's still going to be positive. All right. If I take a smaller and smaller circle, it's positive because things are moving away from this point, right? So ultimately, the right-hand side is always positive, and so the divergence being positive means that your vector field is flowing out of this point, right? This point is a source for your vector field. Okay. If it's negative, then we're a sink. Things are flowing into this point and kind of just, in a way, like disappearing down a drain, in a way. Okay. So divergence of f tells us whether we have a source or a sink. Okay. Now, if divergence of f is 0, then it's neither. That means the same amount of stuff is moving into the point as out of the point. All right. So everybody will have probably seen a picture like this, right, of like a magnetic field. Right. From physics, right? So in this case, what's going to happen is divergence here is positive, and divergence here is negative. All right, at least according to what this picture tells me. All right. Now, what is the divergence here or there? Hard to tell from the picture, right? I haven't made it obvious in terms of the picture. So you could just calculate it, right? Given the formula for the vector field, you calculate the divergence, and that number would tell you whether more things are moving into this point or whether more things are exiting this point. Okay, or it could be balanced, same amount of stuff in and out. All right. Okay, so it's not necessarily, the picture is not necessarily always as dramatic as this. So let me give an example, another picture example. So if I have something like this, where the vector fields are really long on this side, and then kind of, they're still coming out, but shorter in a way, right? So in this picture, it looks like this point is a sink, because a lot of stuff is coming in to this point, but not as much stuff is coming out, all right? All right, but again, in your head, this kind of picture above is kind of a model idea of what the divergence tells you. All right. Okay, so one way to say it is a divergence of f is an infinitesimal version of the flux across a curve, right? It's just what's happening at a single point, right? Divergence of f at, let's say, 1, 2 is, in a way, how much stuff is moving into the point or out of the point 1, 2. All right. Okay, what about the other version? So the other version was curl of f, region, integral c, f dot TDS, right? We just do literally the same analysis, right? You take your point of interest and you take a circle around it, you apply the Green's theorem, right? The right-hand side tells you how much stuff is circling around this point along this circle, right? Now you take a smaller circle, you apply Green's theorem again, right? The right-hand side tells you how much stuff is flowing around this point along this circle. Take a smaller circle, apply Green's theorem again. The right-hand side tells you how much stuff is flowing around this point along this circle, right? Now, as the circle gets smaller and smaller and smaller, you're capturing more and more of what's going on at the point of interest, the center point, as opposed to what's going on outside the center, right? So ultimately, if you think about it like that, the curl tells us how much stuff is moving around our point infinitesimally, okay? So how much stuff is moving around, let me be a little more precise, counterclockwise around our point. All right. So an example of a vector field where we have a positive curl is the rotational vector fields, which perhaps, let's say, looks like this. So here what you can see is at that point, in a way, things are moving around it. All right, the vector field is moving around this point counterclockwise. So you expect the curl at that point to be positive. Let me do a concrete example here. So let's say f is equal to minus y comma x, right? Then curl of f is equal to dq dx minus dp dy, which is equal to dq dx, so dx dx, 1, minus dy dy with a negative sign, so minus 1, which is 2. All right. So kind of our intuition here is correct. Stuff is moving around this point at the center, because the curl is actually 2 everywhere for this particular function. So our intuition at the center is true, but this actually calculation tells me at every point things are moving around that point counterclockwise. And this makes sense because if you look at the structure of this vector field, as you move away from this red point here, minus y comma x gets longer and longer. So even though things are moving kind of like this, out here the vector fields are longer than in here, right? So let me draw a zoomed in picture. So here's our point away from the origin, right? So further away from the origin, my vector fields are actually longer. Closer into the vector field, closer into this point, my vector field is shorter. And again, here's the center, right? So overall, more things are moving like this, right, in this direction than in this direction, which is the opposite direction, right? And so you expect the curl to be positive, okay? All right, so this section is particularly a lot of kind of intuition and trying to understand what it is that this Green's theorem tells us. It's super easy to just memorize the formulas and not really understand what's going on, and that's going to be very difficult, especially in the future when you actually need to use Green's theorem for applications. Okay, let's actually do an application. So how would we, for example, use Green's theorem? Let me write down a conclusion first for what we just talked about. Divergence f equals how much is equal to, let me write like this, flux at a point, right? How much stuff is moving out of that point or into the point. Curl of f is equal to circulation at point. All right, as opposed to flux across a boundary or circulation along a boundary. This is like infinitesimal at a point. All right, so it's kind of analogous to when we talk about average velocity in one variable calculus, when we talked about average velocity and instantaneous velocity. So this is, you can think of it in the same, in analogy. Okay, anyways, let's do an application. So I'm not going to do any numbers here, but let's say we have a semicircular region like this, right? And the question is, what is flux across this region? So here's my region. All right, or across this boundary, across this curve, where a curve goes this way here, straight, and then goes this way here as a semicircle. Let me write C1, C2. All right, so there's two ways to do this. One way is just to literally do the computation, right? Integral C1 f dot n ds, right, plus C2 integral f dot n ds, right? Integral C2 f dot n ds. Again, n is going to be pointing like that and like that for each of these two, outwards pointing. And then you just calculate it, right? Straightforward, something you did in the last hopefully a lot of homework problems from the last section. But alternatively, let's say, so first of all, this might be a lot of work. You're doing two integrals, right? And also, of course, anytime you have integrals, they might be hard for whatever reason. Right? Okay, so alternatively, you can quote Green's theorem. So this is equal to, right? We're going to quote the flux version of Green's theorem, integral, double integral over the whole region itself, the divergence of f dA. All right, so instead of calculating this, so we can calculate, we want this, right? Instead, we can calculate this, all right? And it could turn out that this is easier, right? Again, just in terms of what we've written here, two integrals versus one, so that's maybe one positive. And you can see that this integral, second integral, is easy to set up, just a double integral. You're integrating from the ground to the semicircle, right? Maybe use polar coordinates, depends, right? And then the inside is just divergence of f, pretty straightforward. Okay. All right. Maybe another advantage of doing this area integral here is in order to do these two line integrals, C1 over C1 and C2, you would have to parameterize the curves, right? And that's always kind of a pain, right? Depending on how unpleasant the region is. Okay, so this is always an option that's available, all right? Okay, maybe a more extreme version of this is, I have I have a region like this. Right, and I ask you flux across, again, let me give this a name, flux across C, right? How would you do it? You'd have to do 1, 2, 3, 4, 5, 6 integrals, 6 line integrals. Or alternatively, you can integrate over the region, a two-variable integral, as opposed to 6 individual parameterizations. All right. Okay, this same idea applies as well for the other version of the of Green's theorem, right? Let's say you want, let's do a small variation here. So let's say we have, this is C. The question is, what is circulation of F along C? Right? Okay, so one way you could do this is you do 3 integrals, individual integrals, and you're done, right? But maybe those 3 integrals are hard. Maybe you don't want to do 3. Sounds kind of a pain. Is there an alternative? Well, there is, and that's Green's theorem. And the way you would do it here is, first of all, notice there is no region, so we actually have to fabricate a region. So one thing I could do is just close this up by adding this guy right there. Okay, now I've got a region. All right, and now I can write down Green's theorem, right? Let me call this added curve C prime. Okay, so if I apply Green's theorem, what I'm going to get is the integral over the region of the curl of f r dA is equal to, the right-hand side is the circulation of around the boundary, and that would be comprised of 2 parts. First part is circulation around C, and the second part is circulation around C prime, right? That's the overall circulation. This is the guy we want this, right? And instead, we compute this and this. Okay. And again, then we're done, because if we know this is 5 and this is 3, then we know that this guy over here, which is what we actually want, would be 5 minus 3. All right. So potentially you could save a lot of work this way. In fact, not just save work. Imagine if my original curve C was something terrible like this, right? Which maybe I don't even know how to parameterize, right? This guy is maybe not smooth. So let me just do something like that, right? Maybe I don't even know how to parameterize it, right? So instead, I can kind of close it up and then apply Green's theorem so that I don't actually have to do a parameterization and I don't actually have to do a line integral along this region. Okay. All right. That's actually a very, very common use of the circulation version of Green's theorem. Okay. So let me do one more application. This is kind of a neat trick type of application. So notice this. Let's say I have a region like this, right? With boundary C, and again, we're oriented like that. Let's examine what happens if I just use the simple vector field f equals 0 minus x. Okay, I'm going to use the curl version of the fundamental theorem. You could do, again, this same discussion using the divergence version, and your f would be actually nicer, but I'm going to do it this way because I think this is the more common way to see this. Okay, then what's the curl of f? Curl of f is going to be, actually I want plus here, sorry. Dq dx minus dp dy, which is just going to be, well, dp dy 0, dq dx 1, right? Okay, so let's write down Green's theorem. Double integral, curl of f over region R, dA is equal to single integral circulation ds over the boundary, right? And I guess our book kind of likes to put a loop just to emphasize it's a loop, all right? Okay, curl of f is 1. So this left-hand side is just 1. Okay, what is that? That's the area, right? And what is this right-hand side? F is super simple, right? F is 0, comma x, right? And then we're dotting t, which is dx dt, comma dy dt, right? dt, if we actually write out this integral, t equals a to b, right? So ultimately, this just is t equals a to t equals b. Let me put this equal sign here, of x dy dt, dt, all right? Which sometimes people write, again, in terms of just notation, x dy, all right? The point here is that we actually have an easy way, or we have a nice formula that tells me the area of a region, right? How do I compute the area of this region? I can alternatively compute along the boundary, all right? So I can figure out the area of the region in a way by walking along the boundary, all right? And keeping track of what's going on to a certain vector field, this one right here, as I move along the boundary. Okay. There are actually physical devices that do this for you, that help you calculate area. So there's a physical device. You walk around, let's say a lake. You want to know the volume, or sorry, the area of a lake, right? How would you do it? You have this device. You walk along it, right? And this device physically calculates something like this right here, right? And you don't have to go into the lake, right? Into the water or anything. You just need to walk along the lake. And by the time you come back, you'll have a calculation for the area of the lake. Okay. So even though this is kind of just, it seems like just a neat trick, there are physical objects, physical things that people have manufactured that can help you do, that actually they use to do this calculation. All right. So practical. Okay. One thing you can say is why use 0, comma x? Well, you could have done the same thing with f equals minus y comma 0, right? Same idea. The left-hand side will still be integral of 1. The right-hand side this time will be, let me write this out, 1 dA, right, equals area, equals integral t equals a to b, y d, oops, that looks really weird, y dx dt, right? Which again, you can calculate just by walking along the boundary, all right? Oh, actually, this should be a minus sign here because I have a minus sign right there, right? And this 1 has no minus sign because when I calculate the curl, it's q dq dx minus dp dy. So the two minus signs cancel out. So ultimately, sometimes this calculation is written like this: area equals 1/2 of both of them put together, right? So, and the notation you often see is something like x dy minus y dx. All right. In any case, again, the important thing is you can calculate the area just by walking along the boundary of the region. Okay, a good exercise is to figure out this entire discussion here, except use the divergence version of the Green's theorem. What vector field would you use? Of course, you'll get the same results, but just to see it from a different point of view. All right, one more thing, or a couple more things. So about the curl. So curl of f. What was the curl of f? It was dq dx minus dp dy, right? We've actually seen something like this when we talked about is f conservative, right? We said that we needed to examine whether dq dx is equal to dp dy, right? Let me write it like this: we require this, and this is sufficient if our region is nice enough, right? So this is the same as saying dq dx minus dp dy is equal to 0, right? So is f conservative? Well, we require curl of f to be equal to 0. Okay, so curl of f is related to vector fields being conservative or not. So of course, again, I write require, but if you're in a simply connected region, right? So not a region like this with a hole, right? So a region like this, then curl of f equals 0 is the same as being conservative. Okay, so that's a kind of another way to think about the curl. And all of this fits together and makes sense because let's take a look at this in terms of Green's theorem. Curl of f. Let me write down Green's theorem again. R equals integral c f dot t ds. Oops. Right? If the curl of f were not 0, right, at some point, right, then there's no way you can be conservative because I can take a tiny, tiny little ball around here, right, integrate this guy here over the region, and if curl of f is not 0 at that point, then if I take a small enough circle here, then this integral here is not going to be 0, all right, by continuity. Okay, now what that means is you have a closed loop, right, this tiny, tiny little loop where the circulation is not 0. So loop, so because this is left-hand side is not 0, this right-hand side is not 0, and so we have a loop. So we have loop where circulation is not 0, right? Okay, well, that means you can't be conservative. Right, and we've talked about this a few times already. If you have a loop, right, whose circulation is not 0, that means as you travel along this, the value of your potential has to increase and increase and increase and increase and increase all the way until you get back. So whatever value you started out with, by the time you come back, the value at that same point actually has to be bigger. And obviously a function can have a value can have two different values at the same point, right? And so that potential cannot be kosher, so it cannot be, you cannot actually have a potential, all right? So you're not conservative. Okay, so next section we'll explore the divergence in the curl, except for higher dimensions. The divergence is going to be roughly the same idea. It's still, divergence of a vector field is still going to be a function, but the curl will be something very different. The curl of f will be a vector. All right, so be sure you're kind of aware that in 2 dimensions when we talk about the curl, it's in a way a special case.